Hey, what you doing?
Homework. I have to draw a picture and write 2 sentences about someone or something.
Oh yeah?
I guess I could write about you. What do you do?
You mean like my job?
Yeah.
Well, I'm an organic chemist and I teach at the University of Oregon.
Oh, what's organic chemistry?
Well, it's the study of carbon-containing molecules. How about we go to campus and we learn all about organic chemistry today?
Well, I only need 2 sentences.
Yeah, well, it'll be fun. Let's go to campus.
I only need 2 sentences.
Let's go. Okay, so the first thing we need to understand is what an atom is. So an atom has a nucleus, and inside that nucleus there are protons and neutrons. The protons have a positive charge, and the number of protons that are in that nucleus determines what element it is on the periodic table. So for example, carbon is number 6 on the periodic table. It has 6 protons in the nucleus. It also has 6 electrons outside of that nucleus. And it's the electrons that determine the chemistry. And so organic chemistry is the study of carbon-containing molecules, but carbon bonds to other elements. And so we have to understand how carbon forms chemical bonds to other elements. Okay, so we have the nucleus, positively charged protons, neutral neutrons, and outside of that we have these negatively charged electrons. Now those electrons can be shared between atoms to form chemical bonds. Okay, and if 2 atoms are sharing electrons, we call that a covalent bond. Now when you're forming bonds to hydrogen, it forms 1 bond. When you're forming bonds to oxygen, it forms 2 bonds. When you're forming bonds to nitrogen, it forms 3 bonds. When you're forming bonds to carbon, it forms 4 bonds. And these 4 elements make up a large percentage of organic molecules, particularly if you're looking at biomolecules, molecules that make up you and me, like our lipids, our carbohydrates, our proteins, our nucleic acids, although in addition to those 4 elements, there's a little bit of sulfur and phosphorus, which we can mention later. But we can learn a lot just by looking at the bonding in these 4 elements. All right, so what we have here are some pretty simple organic molecules, starting with methane. So methane is CH4, because carbon forms 4 bonds, and each hydrogen forms 1. And so we can represent this by drawing a carbon in the center with these 4 lines to the hydrogens, where each line is representing a chemical bond. And in terms of electrons, what it means is each bond represents a pair of electrons that are being shared by those 2 atoms. Sometimes we draw this trying to give it a 3-dimensional perspective, because it turns out the central carbon is tetrahedral. And so the 4 bonds to hydrogen are pointed towards the corners of a tetrahedron, like in this model. And so a lot of times we use models to try to visualize molecules in 3 dimensions. Carbon dioxide is another example of an organic molecule. Oxygen forms 2 bonds, carbon 4, And so you can have what are called double bonds. Okay, so here we have single bonds, here we have double bonds. Each bond represents a different pair of electrons. Okay? If we look at a little more complicated organic molecules, we have ethane, ethylene, and acetylene. All of these have two carbons. One has a single bond between the two carbons. This has a double bond between the two carbons. This has a triple bond between the two carbons. Each of these has 4 bonds to each carbon. If you count up around any one of the carbons, you see 4 bonds. And each hydrogen just has 1. Now the shape of these, if you look at ethane, both of those carbons are tetrahedral, just like methane. And you have this single bond that can actually rotate between them. Right? Hold that. For ethylene and acetylene, they don't have that rotational ability. Ethylene is actually planar, and acetylene is linear. And so these are the models for ethylene and acetylene. Now when we get to larger organic molecules, we usually use a shorthand system, okay, where we don't show every carbon, because it gets really tedious if we draw every carbon, every line, every hydrogen. And we draw structures like this, where there's a carbon at the intersection of every single line, unless we write a different atom. Okay, so carbon here, carbon here, carbon here, but here we have an oxygen, here we have nitrogen. We don't show the hydrogens attached to carbon because we know that all carbons have 4 bonds. So we can just fill them in. Like right here, this carbon has 1, 2, 3 bonds shown. That means there has to be 1 hydrogen there. Any hydrogens attached to oxygen or nitrogen, we show those. And so this is the chemical structure of acetaminophen, which is what's in Tylenol. And usually, I mean, a lot of organic molecules have structures of this similar size. But you can have much larger. In fact, you can take these small molecules like ethylene and you can hook a lot of them together to give you what's known as a polymer.
What's a polymer?
Well, it's a really, really large molecule where you just have the same unit connected over and over again. Okay, so there's ways you take ethylene and polymerize it, where you can take one ethylene, connect it to another one, connect that to another one, connect that to another one, until you have a really, really, really long chain. So that we would have just this, the CH2, CH2, as its repeating unit. The N here could be in the hundreds or thousands. So these are really, really large molecules. So if you think about the shorthand skeletal structure we just talked about, it would basically look like this. CH2, 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 just going on very long. And so polymers with this structure, the recycling materials like this is low density polyethylene, which, you know, if you look at the recycling codes on containers, that would be number 4. This is, what's the number on that?
2.
So that's high density polyethylene. So both of these are, you know, structurally the same material. Polypropylene is where you have not just CH2, CH2, but you have a CH3 group sticking off of every other carbon. And that would be something like this, right? Number 5.
Mm-hmm.
And polyvinyl chloride, you have a chlorine on every other atom in the chain. Again, really, really long chain. This, number 3, that's made out of polyvinyl chloride. And if you have this 6-membered ring, you know, 6 carbons in this ring on every other carbon on these really, really long chains, that's polystyrene. Here's an example of polystyrene. Now, all of these polymers have carbon backbones, right? They're really, really, really long chains of carbon. It's possible to have other polymers where you have other atoms in the chain. Right, there are some polymers that have atoms other than carbon in the backbone, like the 2 on the board here. They have oxygen in the backbone. And having oxygen in the backbone actually makes it easier for them to be recycled. Those carbons that have, those polymers that have really long carbon chains, they tend not to break down in a reasonable amount of time, and they get like stuck in the environment when people throw them away. We can do chemical reactions with these, and in fact I have my students do a chemical reaction with this particular polymer to return it back to the starting materials. So to take this really, really big molecule, do a reaction, and return it back to the really small molecules. Polylactic acid is a polymer that's made from corn, and so you ferment corn, and you get lactic acid, you polymerize that, and you get this as a repeating unit, but when you put that back in soil or compost it, microbes in there are supposed to be able to eat it and metabolize it, and so it doesn't last in the environment for a long time. Pretty cool, huh? So how would you like to learn, let's say, well, I teach the first quarter of organic chemistry, 10-week course. I could teach you right now the first 10 weeks.
10 weeks? I have school on Monday.
Well, how about we just do it as a montage then?
Montage? How long does that take?
We could make it take about a minute.
Okay.
All right, let's do it. Let's do a montage. All right. All right, well, it looks pretty good. Looks like you learned first 10 weeks worth of material. You want to go into the lab and look at some compounds?
Sure.
All right. Did you know that jellyfish are fluorescent?
No.
They are. And in fact, there's a protein in them that has a small molecule that fluoresces green. The protein structures shown here is just a big molecule. It's a polymer. It's a polymer made up of a bunch of amino acids. Okay, and it folds into this shape, and a couple of them cyclize to give you this fluorescent molecule. Now we can go into the lab and we can make molecules that look like this. And we can do that. Not only can we do that, we can change groups on there, and we can change the color that it fluoresces. In fact, we can control that. And this is really what synthetic chemists do, is that they synthesize compounds that have new functions, new properties that you don't just get in nature. And so, you want to go into the lab and look at a few of these?
Mm-hmm.
All right, let's do that. So we're in the lab now, and we have 4 different of these green fluorescent protein chromophore derivatives. And you can see the structure on each of these. And what I'm going to do is I'm going to take a tiny bit of each one of these, and I'm going to put them, I'm going to smush a little bit of it onto a piece of filter paper, and then we're going to look at it with a UV lamp. All right, so what I did was to take very small amounts of those 4 different compounds and just smush them onto a piece of filter paper. And you can see what they look like under normal light. Now we're going to look at them under UV light. We're going to turn off the light. So Henry, turn off the big light. And now you can see them under UV light. They're fluorescing, and they're fluorescing different colors. So there's one that's kind of green, one that's kind of light blue and orange, and kind of a dark grayish blue one. And again, the only difference between these is the group that's attached to that ring of that green fluorescent protein chromophore. So we can put different groups on there, and we can effectively control the color. We can make non-natural fluorophores of pretty much any color we want. Isn't that cool?
Mm-hmm.
So, you want to go home now?
Yes.
Okay, so why don't you go ahead and write that report on organic chemistry?
Okay.
All right.
Dad, I finished the report.
Oh, so you're done with the report?
Mm-hmm.
All right, let's see how you did. Oh, this is awesome.
Thanks, Dad.
All right, can I hang this in my office?
Mm-hmm.
All right. Well, that's been a fun day learning about organic chemistry.
Mm-hmm.
All right.